I'd like to introduce Michaela Toffer, who is a colleague at the University of Tennessee. She's the co-chair for this meeting and is the chair for next ISC. I have to say I'm deeply honored to have this award named after me. I join Hans Moyer Award and also the Price Award, I guess, in that context. So let me turn it over to you and explain the situation.
Thank you, Jack, and it's quite an honor to be here. And being the chair of this committee, there are two thank you notes I want to share with all of you. The first one is for the committee. I was very fortunate to work with an amazing group of international colleagues who helped us to select the winner today. The second thank you is for you, Jack. And it's not just from me, but on behalf of many of us, because you are for us a role model and a mentor. And there is something I want to share with all of you, that when ISC approached Jack to ask, what about creating an award in honor of all your work you've done, and you're still doing a lot. So
not quite dead yet.
Yeah, no, we are looking for more. But ISC reached out to Jack, and Jack said, well, yes, but it has to be an award for colleagues that are in their early career, new talents in HPC. So that tell us how much you care about the future of HPC and the talents that are among us. So said that, today we are celebrating one of us, a talent in HPC, Torsten Hoefler, who is the recipient of the 4th Jack Dongarra Early Career Awards. You are telling us about your vision of HPC and HPC at the Crossroads, and we are looking forward to learning more about.
Thank you very much. Thank you very much, Michaela. Thank you very much, Jack. I'm deeply honored that I'm receiving this inaugural Jack Dongarra Award, representing one of the lighthouse in our community. In fact, my favorite Jack story is when I first met him. So I met him as a young student. I was literally just coming off the master's, and I met him in Italy at a small conference. And at that conference, they were serving only wine for breakfast, for the breakfast break, for lunch, and for the afternoon break. And right after the afternoon break, I had to give my talk. Of course, after being served 4 rounds of really good Italian wine, I was barely holding on to the wall next to me, and I was hoping nobody would show up, honestly. And then, of course, Jack walks in and sits in the first row, and I'm like, oh, God, no. And I gave my talk. I feel it went well, but I don't really remember. But what I remember is at the end of the talk, Jack actually asked the first and only question, and I could not answer it. And I went, oh, yeah, I'm sorry, I think I had too much alcohol. And then Jack was laughing, exactly like he's laughing right now, basically saying, yes. That's how we go. And then I thought, this is the community I want to join. So it is a wonderful, a wonderful opening to my career. And we're here to commemorate Jack's impact on high-performance computing. And if you ask him himself, he would tell you that it's along really 3 major dimensions: libraries, the message passing interface, and benchmarks. So we all know that Jack has developed lots of libraries, and I don't want to repeat those. I have asked an artificial intelligence to come up with a logo for his very first library, IcePack, though, and the German speakers will appreciate this among you. But that artificial intelligence is actually very much based on the implementation of Jack's BLAS library that was later extended to deep learning workloads, where much of artificial intelligence actually bases on. Then the message passing interface. So we all know the message passing interface. I don't need to say much more. I want to use the opportunity, though, to memorize one of the members of our community here, Rusty Lusk, a good friend of Jack's, and also a friend of mine, who was unfortunately taken too early from us. But, well, I would also want to talk about Jack's achievements in the benchmarking area, which we've just heard, the top 500. So there's nothing but the top 500 in our community. Here, I also want to use the opportunity to commemorate Hans Meurer, the founder of this very conference. We are sitting here, one of the co-founders of the top 500 list. So now, the question is, you may be thinking, why is this guy here? Why is he talking about Jack? Well, because I've been following Jack's footsteps as one of my mentors and inspiring personalities in the community along these 3 dimensions, roughly. So let me start with the first one, the libraries. So libraries, I really see as a performance programming abstraction. So in the sense that performance engineering is hard, and very often it leads to extremely hard to understand code, and we start from some simple code like this one. So this simple code is just, well, you immediately see it's a matrix multiplication written in Python, because everybody writes everything in Python these days. And it may not run fastest, but actually, if you're a good Python programmer, you wouldn't write a matrix multiplication like this. Some of you are already thinking like, you would actually write it like this, because that is a much more productive way of writing it. And in fact, a good Python implementation would be invoking a dgem for that little equation. And of course, Jack's dgem. So now the scientist is happy, everything is great. The problem is, not everything we are doing maps to libraries. So looking at this code, very similar code, very similar structure, same iteration space, also written in Python. All I'm doing is to replace the addition with a multiplication and the multiplication with a maximum. Some of you already think, oh, that's a semi-ring. Yes, it's a semi-ring. It's not the tropical semi-ring, so it doesn't have a library implementation. So that is not the problem. How do we work with these kinds of codes, where we always have pieces in them that cannot be optimized by libraries? And they will hit you hard with some subtle form of Amdahl's law if you don't really accelerate those. So what you would do is you would optimize that code with something like an I/O optimal schedule or something else that, for example, in this example, based on our work on Cosma, you could make this code really fast. And one of my brilliant students here, Grzegorz Kwaśniewski, was actually helping with that. But what was he doing to make the code as fast as a gem call? Well, he was generating, somehow automatically, nearly 1,700 lines of source code for Cuda devices. So that's something that the average scientist is not willing to do, to translate your one-line statement into 1,700 lines of code just to make it fast on a device. Right? It's semantically absolutely equivalent. So libraries are great if they apply, but somehow we need something that helps us to apply to arbitrary programs that cannot be defined by libraries. So here I would like to introduce performance metaprogramming as a concept that somewhat enables us to generate our own libraries. So let me talk about that a little bit in the high-level overview. So what is performance metaprogramming? At the general vision, you have a domain scientist that he or she writes code in a language that is close to the domain. So ideally something like MATLAB, NumPy, even Fortran, PyTorch, or other domain languages that are easy to understand from a semantic perspective, easy to express the problem of the scientist. Then you have some kind of translational applied scientist that translates that into an internal representation, and this is where the key lies. This is why it's highlighted, the internal representation. So that internal representation is where the performance metaprogram is actually applied to. So you translate your code into an IR. In our case, it's a data flow graph-based IR, but that's a detail. At the high level, there's a performance engineer now, a different role, who writes programs that input the internal representation that is close to the scientist, and output the internal representation that is close to the machine, and then at the end you generate machine code. So it's really metaprogramming in the sense that you write programs that optimize programs based on a description, a data flow description in our case of that program. So what does that mean? Well, we have tens of lines of source code ideally for the domain scientist view. And if you've written any TensorFlow code or PyTorch code or any deep learning, well-designed deep learning framework code, you see it. Like a transformer model that is driving all of AI fits on 20 lines of code. 20 lines. And I've written it myself. It works. It works actually reasonably fast on a GPU because it is backed by libraries. So now we take these 20 lines of code that drive all of AI today, essentially. And of course, at the end, this is much more code to make it fast. I mean, Jack knows this all very, very well. So, but now, if it's not supported by libraries, we can use this performance metaprogramming approach to write hundreds of lines of code that transform this internal representation resulting from the tens of lines into a very large representation, typically with thousands or maybe even tens of thousands of lines of code. So that is the high-level idea of performance metaprogramming. So we've, of course, implemented this, tried this, and well, I want to show you some early results here. I mean, one of those results is taking the FV3 code that was developed at NOAA together in a collaboration with the Allen Institute of Artificial Intelligence and the Swiss National Supercomputing Center, led by one of my scientists at the time, Tal Ben-Noon. He was also the architect of DACE, to accelerate that code. That code was, as I mentioned, rewritten in a Python high productivity language. So it required rewriting that code, which was done mostly by AI2 in that case. And then we compiled it to a GPU and got a speed up of 4. This is somewhat what you expect. So we see GT4Pi as the framework that was developed by CSCS, and AI2 implemented the code. We put DACE underneath it and made it 4 times as fast. That's great if you want to rewrite your code. But who wants to rewrite his or her code? Of course, nobody, because if you have a lot of Fortran code, which we do, you don't necessarily want to do this. So our latest experiment was actually looking in a collaboration with ECMWF, the European Center for Medium-Range Weather Forecasting, very similar domain, also climate and weather sciences, at one of their key applications, which is called Cloud SC. It's the Cloud Microdynamics application, which is fully written in Fortran. And actually, they like Fortran. The domain scientists do enjoy writing Fortran code. Well, sometimes you wonder why, but so one of my postdocs, Alexandru Călătoriu, actually imported that Fortran code into our DACE framework. And the nice piece of this is that we have various versions of this Fortran code supplied by ECMWF. So we have the original version in blue, which is hand-tuned code to CPU, hand-tuned, all hand-tiled, fast. We have a hand-tuned version in C, which is green here, which is slightly slower than the Fortran version, and we have the mostly automatically generated version in DACE, which is also slightly slower than the original Fortran version. So now you wonder why. Okay, now we have translated that to a different representation and get it slightly slower on a single core. Well, one lesson to be learned here is that Fortran is actually really fast when it comes to single core. So it's really hard to beat. But of course, we don't run single core. Now, if we zoom into that very low part here on the right, we run it now on 32 cores, so we get substantial speedups. We get substantial speedups for both the Fortran as well as the hand-tuned C version. Both of them have been hand-tuned for OpenMP parallelization, and now the DACE version is slightly better. Why is that slightly better? Well, because we could pull a trick that the scientists or the performance engineers who optimized these other codes could not or did not see. So now, of course, you're all saying, well, multi-core, great, but we're talking about accelerators. We're talking about GPUs now. Well, let's zoom in again in this diagram at the very bottom, and let's now look at the speed up we could get out of a GPU. So now we are again comparing these 3 different implementations, the DACE version, which is now 100 times faster than the single-core version, right? And now the Fortran plus OpenACC and the hand-tuned Cuda version, which was a complete rewrite, taking many months of an ECMWF performance engineer. But we see the pretty much automatically generated version from the original Fortran code, including a performance engineer, is nearly as fast. So it's not faster in this case, but it's nearly as fast. We believe in 2 weeks this will be faster. So we're still working on it. But the effort we had to invest into this, besides writing the front end, was about 2 weeks and not multiple months. So now this performance metaprogramming is actually quite a powerful concept going forward. And the last piece I want to mention here is a result that is already 2 years old, actually 3 years old at this point. One of my students, Alexandros Tsiogas, was getting the opportunity to run at Full-Scale Summit, thank you very much, Oak Ridge, at the time, and run a code that was also written at that time partially in DACE with the same principles. And that code was actually a Gordon Bell Prize finalist twice, and once an honorable mention. So it was not the run-of-the-mill code, it was a highly tuned code. But with the framework, we looked at the data flow and we found that you had to swap 2 loops that were more than 10,000 lines of code apart, which a performance engineer is really hard to see if they're that far apart. So by swapping these 2 loops, we essentially got a speed up of more than 100x over that highly optimized code. So that now sounds quite trivial, but it took a long time to understand this. And that earned us the Gordon Bell Prize in 2019. Also with the similar mindset of that performance metaprogramming, turned it into a different representation that is meant for performance engineering. So what I really want to communicate here is that these original languages that we are using, like C, C++, Python, they may not be the right language to reason about performance. They're the right language to express a problem. Fortran, formula translator, they're to translate formulas. They're not to optimize codes. Optimizing codes is a different business. And this is why we propose to work on a data-centric representation to optimize codes, because much of that is limited by data movement. Okay, now let me move on to the second piece, MPI. Many of you who know me know that I've been investing a lot of time in MPI in my early career. This is, in fact, the talk I was mentioning at the beginning, where I met Jack first, was an MPI talk. I don't have enough time to talk about all the areas that we've explored there in the past, but actually, there's a book on it, so you could just read it if you want, with my co-authors, Bill, Rajiv, and Rusty. May he rest in peace. There's also a tutorial that we've been giving yesterday, so you already missed it. But this will be given at every ISC and at every SC as long as the conferences want, and I'm in business. But what is new now? MPI is mature, but let us go a little bit deeper. Let us go one level below MPI, because we have been observing a tremendous change with the acceleration in compute, with the introduction of Cuda, which has literally driven the AI field. So now, why would we not apply a similar principle to the network? So what I want to now discuss is what I call Cuda for the network, or accelerated networking. The observation is that today's architectures are not very good in data processing, like today's CPUs, especially not streaming data. Very much like the observation that matrix units on GPUs would be much more efficient way back when, like 10 years ago. So let me now introduce an abstract machine model that we could use to exploit that observation to build a network acceleration protocol and engine. Now I'm talking about the protocol, and the engine comes in a minute, of course at a very high level. So what do we have as an abstract machine model of a network card? Now this is not a GPU, this is not a CPU, it's now a network card, because it's also a form of data processing device. In fact, its job is to move data. So this network card has a fast shared memory packet input buffer. Every card has that. It has a scheduler where packets come in and are scheduled to this fast shared memory. Every network card has a set of processing cores, which I call handler processing units here, but they're usually not exposed to the user. We have an outbound interface to send messages, and we have a DMA unit to move data to the main CPU, of course, into some form of memory. So here we see various forms of memory. We have CPU memory, we have DRAM, and we have NVMe memory. Of course, like in Cuda, you download your kernels, and we call these handlers, to the network card for acceleration. We also manage the memory on the network card exactly like in Cuda. So it's really, up till now, kind of a one-to-one copy. The differences will come very soon. So how does it work now? Well, it works very differently from Cuda. You're not invoking kernels, because kernels are actually invoked on incoming packets. Because the network card is a reactive device. It has a pipe, packets come in. These packets are deposited into the fast shared memory of the card. Then they're scheduled to these handler processing units. Then they're processed by these handler processing units. Some packets leave the network card back to the network. Some are committed into memory. Some are committed into non-volatile storage. So it's just everything that is DMA accessible I can work with. So now, what can we do with this? Well, we can actually offload protocols. We can enforce policies. We can do data processing on the NIC quite effectively. So I want to give you one example of a file server that we could be employing in a data center, or even on Azure, or on a high-performance computer. Here's just a write request that comes in. Of course, it comes in as a packet. It moves in the state in the buffer. And then the first packet is processed by a header handler, the first packet of this request. So this handler is just executed once per request, once per write request. But we all know that a write request of data to a file server could be multiple megabytes or even multiple gigabytes. So meaning that there may be, or most likely are, multiple packets in this case. So each of these packets also moves through our abstract machine here and is processed by these handler processing units, invoking the payload handler, which is now invoked on every single packet. And at the end, once the request is done, once I committed the, let's say, gigabyte of memory into my main memory or NVMe, then I can execute a handler that sends a reply, which is the final handler. So this is the programming model in a nutshell. It's slightly more complicated, but this is the programming model from a Cuda perspective. So you have 3 different kinds of handlers, not just one kernel. But okay, does this work in practice? Well, we have shown that this works in practice by building a hardware NIC, essentially. It's not taped out, but it could be taped out, based on the Conundrum interface, or on the Conundrum NIC, where we look at the processing unit that I just talked about. This is in collaboration with Luca Benini, who's also giving a keynote at a workshop on Thursday, I believe, at this conference, and of course my student Salvatore, who has been driving that whole project. So it's I was just going to say a standard RISC-V CPU that we're employing there, but it's not standard. It doesn't have any caches, Because for network packet processing, stream processing, you don't need any caches. Caches are more harmful than good in this case. It has scratchpad memories. So every data movement is explicit in this machine. That's the only thing I want to say about it. There are more optimizations, but I'm running out of time. But this has actually been synthesized in the Global Foundries FDSOI process 22 nanometers. It clocks at about 1 gigahertz. It is very small. There's only 100 million gates. And we have a lot of gates, so which is about 18 square millimeters. But in fact, if you look at NIC chips today, they have about 400 square millimeters for the whole thing. So it's relatively small and relatively cheap this way. So you could take it, you could implement it, and you could run with that model. There are multiple companies actually looking at this pretty seriously. Now let me get to the last part, the benchmarks. Last part where I'm following Jack's footsteps. And of course, there it's impossible to follow. I mean, the top 500 is the thing. But I would like to focus, I was focusing my career on a slightly different aspect of it in these benchmarks. So the idea, or my observation was, that it was extremely hard to reproduce performance. To reproduce performance on a supercomputer, and it's still extremely hard. Like, imagine you're running a full-scale job on your favorite supercomputer today, and imagine tomorrow there comes a software update that halves your performance on that supercomputer for whatever reason. You cannot roll back that software update, and you're just lost. By the way, that happened. Thank you, Cray. It happened like a week before the deadline. It's even worse in this case. So. You cannot reproduce this performance. Even worse, the supercomputer may be decommissioned. For example, if now I wanted to reproduce the Gordon Bell run of 2019 that we received the Gordon Bell Prize for, it would be impossible. We cannot do this. Like, this machine does not exist in that configuration anymore. So we came up with a set of rules where you basically try to circumvent the problem. It's not solvable because science bases on reproducibility. But what we advocate is looking at interpretability more. And you could look through these rules that kind of help you to report performance results in a way that people can later reason about what has happened, even though the system is not available for reproduction. Right? Then, of course, data science happened. And people suddenly started to care about the performance of data science workloads. And then, of course, the typical thing happens. Well, you can come up with many ways to make your performance on data science workload look much better than it actually is by exploiting several data science facts. And this is very much like the original paper, 12 Ways to Fool the Masses, but specific for how to not do things on data science workloads. We still have to work on the actual constructive paper that shows how to do it right. If you're interested in one of these things, I would recommend you to look at the first ACM conference on reproducibility and replicability next month, where I'm honored to give the opening keynote with topics like this. Okay, with that, I would like to close that first part of, the second part of the talk, where I introduce performance metaprogramming and Cuda for the network and performance as a science, essentially. But now, as we've just heard in the keynote, HPC is at a major crossroads. And I want to use that opportunity to make 3 of my personal predictions that I believe are coming true in the years to come that will have a big impact on the community and also to the young scientists. Many of you are young scientists. That would be a focal area where you could look at. It's certainly a focal area where I'm going to look at. Prediction number 1 is actually networks will converge. What does that mean? Well, cloud networks are a gravity well from a vendor perspective. If you don't have a product that can also go into a data center, there is a problem. And HPC will most likely follow incidentally, because who's building the biggest computers today is unfortunately not us anymore. The biggest in terms of number of nodes. The network performance is a different business. Okay? So here we have actually published a paper in 2022 together with Ariel Hendel, the chief architect of the Tomahawk switch, which at the time was the most deployed data center switch chip in data centers. And Duncan Rowath, who's one of the architects of many of the Cray networks that we know, like Slingshot, Arius, and those. And we have been sitting together looking at the ways we could converge these 2 industries, looking at the differences, looking at the commonalities. And it turns out that the final prediction of this paper that was published in IEEE Computer is actually that they could converge. They're not that different at the end. And it would be a much bigger and better market for all of us, for the data center providers, the high-performance computing community, and the network the network vendors. Later, we went on to actually look at the differences between high-performance computing and data center in the sense of on-prem HPC systems and cloud-based HPC systems. And we found that in the cloud today, many of these architectures are actually the same. It's really just a difference in business model. It's all about money at the end. The cloud is all about money. There's, like, technologically, you can just roll a supercomputer into the cloud, and then if somebody buys it, you can make money with it. That's it. Other cloud vendors like Google and Amazon are on their own road. They try to use their own networks. They don't roll supercomputers in the cloud. But still, those are now high-performance networks that they're selling. So that is something to be considered. This study was done under the lead of Daniela, one of my postdocs. And it's quite a nice study. I would recommend reading it. It appears at Sigmetrics next month. And then the last one, or the latest work in this area, is a very specific criticism of how we do RDMA in data centers today. The criticism of RDMA over converged Ethernet, which is one of those technologies that looks more like duct tape than anything else, but it had to go fast and it had to bring all the benefits of Ethernet into RDMA, I apologize, all the benefits of RDMA into the Ethernet data center world. And we have a specific set, together with lots of hyperscalers and vendors for hyperscalers, a specific set of criticisms where we could increase the usability of these networks in HPC as well as in the data center. Prediction number 2 is accelerators will converge. See, it's all about converging. And actually here, the subtitle is the attack of the killer tensor cores. Right? You all know what that means. We've heard it this morning. These tensor cores, they will just take over. These supercomputers will literally be eaten by the tensor cores. By the way, all of these images come from an AI that used very little descriptive input to generate these funny comments. So what does that mean in practice? So in practice, we could just listen to Lisa Su, who this year at ISCCC was giving the keynote and talked about a 30x difference in terms of energy consumption when going from FP64 to FP8. 30x. You would suspect 8x because it's 8, but no, it's actually 30x. So we will be happy. We will be lucky if we are getting FP64 in 5 years, because everybody is going there. Furthermore, Jensen was making a similar statement, but he already has a product. If you look at the performance difference on the Hopper architecture between the FP64 tensor cores and the FP8 tensor cores, it's also 30x. So there seems to be something magical about the 30. AMD and NVIDIA are agreeing on the same number. So, of course, this is not the end of the story. We will have more hardware support for vector scaling, 0 point, structured sparsity, all stuff I cannot really talk about here, but you could look at those offline if you follow the work that my lab is doing. Furthermore, as we go smaller data types and higher performance, we will be more data movement limited. Gets even worse. So we are already data movement limited, but we'll be hit by latency, we'll be hit by sparse connectivity, and there's 2 solutions where you could ask Bob Wisniewski about memory-coupled compute or Microsoft about how to deal with the cost of networks going larger. The last prediction is really programming and tools converge. Data science is the gravity well here, and HPC will follow. What does that mean? Well, the most popular language in March 23 is Python. You wouldn't believe it. It's Python. And we have been making, at least I have been making jokes about Python in the high-performance computing context, saying that it's the slowest language you can imagine. It's interpreted. It has all kinds of horrible things from a performance perspective. But it is the biggest ecosystem for scientists, for data scientists. So what I believe with these 400,000 packages, what I believe is that we as a community, we have the duty to help these data scientists to succeed. We don't have the duty to teach them to use our tools. We have the duty to help them to succeed, and we have to make Python fast. So parts of this is actually going on. I mentioned DACE, so DACE is also a Python translator. Other communities are doing this with PyTorch. We have grid tools at CSCS, so this is actually going forward. So with that, I would like to come to the end of my talk and really want to thank all of my mentors in the great HPC community, mentors who helped me to grow, who helped me to get to this stage explicitly. Furthermore, I want to thank all of my friends in the community, which there are too many, and I apologize if I forgot anybody. These friends, they have been helping me in hard times and also in easy times to have more and more fun. But at the end, and really foremost, I would say, I want to thank my research group at ETH Zurich and elsewhere, who have been really fearlessly putting my crazy ideas into practice and helped me to build all of those. I've showed some faces, but you can see there are many more people involved than I was actually showing on the previous slides. So with that, let me just summarize. I believe performance metaprogramming is going to come. I believe we should be looking at Cuda for the network. I also believe we should be improving our science strategy or our scientific thinking when it comes to benchmarking, performance benchmarking. If you're interested in any of this, we have more than 180 videos on our YouTube channel from my group members and myself, where you can look at every detail of the talk, because it was very short, I understand. And if you even want to get more involved, join us as visiting scholar, a PhD student, or postdoc. So thank you very much, and I give it back.
Thank you. Thank you, Torsten, for this fantastic talk, and thank you to all of you for being here to celebrate with us the success of Torsten's. We have a lunch break now until 1 p.m., followed by the very popular vendor showdown session. Don't miss it, and many, many interesting buffs. So enjoy the rest of the conference.